In the modern world, with all its technical requirements, there is an ever-increasing need for motive power. Probably the most economic way of obtaining power is the harnessing of water. But in many places, water is scarce, while in others it simply does not exist. Another source of power is coal, but coal supplies are concentrated, and this raises big transportation problems. For wherever man lives, he needs fuel. Oil, too, is a source of power. Like coal, it can generate heat and thus drive engines. The source of power is only one problem. There is also the question of getting the necessary quantity into a confined space. Take the automobile, for example. Here, the ratio between the fuel volume and the remaining useful volume is excellent. With aircraft, this ratio between fuel volume and useful volume is much less favorable. And with the rocket, where the maximum amount of power is required in the minimum of space, there is hardly any useful volume left. Fortunately, there is still another source of energy, the latest to be discovered: atomic energy drawn from the nuclei of atoms. The fuel of nuclear power stations is developed from the atoms of uranium. These stations can deliver power to cities. This source can cover part of our needs. But there is still another and more powerful source of nuclear energy which can supply our needs for millions of years to come. This source is water itself. Water is composed of molecules, and each water molecule made up of one oxygen atom with its nucleus, with 8 electrons orbiting around it, and 2 hydrogen atoms, each with its nucleus and 1 electron moving around it. The type of hydrogen we need has a different nucleus. Only 1 in 7,000 atoms is a heavy hydrogen atom. The heavy hydrogen atom is chemically identical to the normal hydrogen atom. but its nucleus is different. It contains two particles, hence its name, heavy hydrogen. These two particles are called a proton and a neutron. The proton has a positive electric charge and is in fact the nucleus of a normal hydrogen atom. The neutron has no charge at all. It is therefore a strange fact that they stay close together, although they don't attract each other electrically. Now, let us suppose it is possible to observe the behavior of two protons in the process of being pushed towards each other from a distance. The closer the protons get, the greater the force of repelling between them becomes. If they're brought very close together, the mutual repelling force becomes tremendous. And if the forces pushing them together are suddenly removed, this is the well-known phenomenon of the mutual repulsion of bodies which have been charged with the same type of electricity. But if we could now increase the forces still further and bring the particles very close, then they suddenly combine. This occurs because a binding force appears between them which is very much greater than the electric repelling force. This binding force is called the nuclear force. It only becomes active when the particles are very close together. The true nature of this force is unknown. Since a neutron has no electric charge at all, no force is required to combine it with a proton. This is the nucleus of a heavy hydrogen atom. If we wish to reverse this process and separate the nucleus, we have to overcome the very powerful binding force which now exists. Another way of putting it would be to say that the nucleus possesses a certain amount of negative binding energy. To make the idea of positive and negative energy clearer, let us take two magnets. It is well known what happens when two magnets face each other with the same pole. A force is needed to bring them together. And when they're released, they separate with great speed because of their repelling force. The magnets, when pressed together, possess a quantity of positive energy, say, plus A. It is called positive because energy comes free when they're released. But if we reverse one of the magnets, the opposite poles will face each other, with the result that the two magnets attract each other. Now, the magnets possess a certain amount of negative energy, say minus A, because work has to be applied to separate them. So here, the set of magnets possesses positive energy, because energy comes free, and here, negative energy, since energy has to be applied to separate them. In the same way, the nucleus of a heavy hydrogen atom contains a certain quantity of negative energy, say minus B, because energy has to be applied to separate the particles. Before proceeding to the problems of making use of these energies, it is necessary to study more complicated particles. Also, in water, we find very rare hydrogen atoms. They have one proton and two neutrons in the nucleus. Each particle is bound with a binding energy of minus B to the others. So altogether, the negative energy amounts to minus 3B. To split this nucleus completely, an energy must be applied of plus B. another plus B, and another plus B. So altogether, an energy of plus 3B has to be applied. Now suppose a neutron comes close enough to a heavy hydrogen nucleus to form a 3-particle nucleus. Then the total binding energy has suddenly become minus 3B. The energy balance of this reaction is favorable. We started with a nucleus having an energy content of minus B. We added a neutron without energy content, and we got a nucleus with an energy content of minus 3B. Comparing left and right-hand sides of this reaction, we find this equation can only be right if an energy quantity of plus 2B is set free in some way. Unfortunately, there are no separate neutrons. However, there are other ways of getting this required reaction. Suppose we cause a collision, or better still, a fusion between two heavy hydrogen nuclei. This will create a 4-particle nucleus. But this is only an intermediate state, since it splits up into 2 parts, a 3-particle nucleus and a proton or a neutron. Have we gained anything at all? Yes, we've gained an energy quantity of plus B in the form of kinetic energy of the reaction products. But how can this fusion be realized? We must remember that protons repel each other, so there seems only one solution: to increase the velocity of these particles so that they get close enough. We can do this by increasing the temperature. This means higher kinetic energies of the heavy hydrogen nuclei. But it is only when the temperature increases to 10 million centigrades and more that we get the required result, fusion. The energy gained is liberated in the form of kinetic energy, the speed of the resulting parts. This means that when this fusion takes place, the temperature of the hydrogen gas will rise, rise, and rise. And the energy gained will be liberated in the form of more kinetic energy. If we can harness the results of this fusion and transform their energy into electricity, then the sea will be our supplier of power for millions of years to come. But how are we getting power from the atom today? We know that the atoms we have mastered are less powerful than those we can get from the sea. Nevertheless, the energy we have obtained from atoms is very considerable. It is well known that all matter is constructed out of elements or combinations of elements. There are about 100 different elements, of which ordinary hydrogen is the lightest. Its nucleus contains only one proton, and there is one electron orbiting around this nucleus. The chemical behavior of an element depends on its number of electrons. There are as many electrons in the atom as there are protons in the nucleus. An example is carbon, with 6 protons in the nucleus and 6 electrons orbiting around it. There are also 6 neutrons in the nucleus. A heavier element is silicon. It has still more protons, 14. Copper has 29 protons, and the metal uranium, 92. Thus, the uranium atom contains 92 electrons, and in the nucleus there are, in addition, 146 neutrons. We all know that the lightest element is hydrogen, element number 1. 1 electron in the atom, 1 proton in the nucleus. The second element is helium, and so on. But can we use these larger atoms to gain energy? Let's investigate fusion of them and see what happens. First, let us repeat what happens in the fusion of heavy hydrogen nuclei. There we found that energy is needed to make the nuclei collide. A very high velocity of the nuclei, or in fact, a very high temperature to fuse the atoms. In order to start this reaction, we have to apply energy in the form of heat. As a result, we obtain energy in the form of more heat. We can symbolize the balance of energy with generators. A small amount is required to start the reaction, and a huge amount of energy comes out of it. Let us now try to fuse heavier nuclei. When nitrogen nuclei, each containing 7 protons, are made to collide, and the same energy per hour has to be delivered as with heavy hydrogen, more energy is required to start the process. In the case of still heavier nuclei, such as chromium, each having 24 protons, we will need still more energy to keep the process running and deliver the same energy as heavy hydrogen. In fact, one has to put as much energy into the process as one gets out of it. This can be seen with nitrogen. A certain amount of energy is required to bring the nuclei together. This energy corresponds to the 2 groups of 7 protons. With chromium, we need a higher amount of energy corresponding to the repelling action of the 2 groups of 24 protons. On the other hand, with nitrogen, we gain the binding energy of this contact area, which is smaller than with chromium. Now, the energy that must be applied to overcome the repelling action of the protons increases far more rapidly with the size of the nuclei than the binding energy that is gained. In the case of still heavier nuclei, such as silver, each containing 47 protons, far more energy is needed than is delivered. So we have to reverse the process. This is what really produces energy in the nuclear power stations: fission of nuclei. We must split big nuclei. After such a fission, the 2 parts repel each other by virtue of their protons and fly apart with great speed, colliding with the other nuclei in the neighborhood. So kinetic energy is distributed over the whole area, which means heat. In many nuclear power stations, uranium is used in the form of bars. If there are enough fissions in the bars, considerable heat will be produced, the uranium bars becoming very hot. A liquid or gas is then pumped along these bars. It immediately becomes heated, and on passing through an exchanger, turns water into steam. This, in its turn, drives a turbo generator producing electricity. Now the question arises, how is fission accomplished? Suppose that the nucleus of a heavy atom, for example, uranium with 92 protons and 146 neutrons, should, for some reason, contract. Then all the positive protons in the one part will start repelling all the protons in the other part. If the contraction becomes stronger, this means that the repelling force becomes bigger than the binding force of the few particles in the contraction area. They will, therefore, fly apart with great speed. It appears that with fission like this, 2 or 3 neutrons come free, and these move away at a slower speed. Let us see what happens if there are other uranium nuclei in the neighborhood. The neutron may hit this nucleus by accident. In such a case, the negative binding energy of the nucleus suddenly becomes greater, because the neutron is bound to all neighboring particles. Greater negative energy means that positive energy must have been freed. As it is, the freed energy reveals itself in the vibration of the nucleus, which in its state could lead to the contraction and thus to fission. If, however, the speed of the neutron is too high, another neutron will be knocked out of the nucleus at nearly the same speed. In practice, measures are taken to ensure that the neutrons first collide with atoms other than uranium. This is done to decrease their speed to the velocity required to cause a uranium fission. And now let us focus on this nucleus and see how fission actually takes place and how the fuel of the future is used today.